Did you know that before dinosaurs ruled the Earth, there were creatures so massive that they make today's largest animals look like toys? We're talking about dragonflies with wingspans of 75 centimeters, millipedes over 2 meters long, and scorpions the size of modern dogs. But here's the most mind-blowing part: these giants thrived in an alien world where oxygen levels were 50% higher than today, creating a planet that would be toxic to most modern life. Imagine if I told you that 300 million years ago, you could have walked through forests filled with 40-meter-tall trees that weren't even real trees, while avoiding car-sized spiders and cockroaches as big as house cats. This was the Carboniferous Period, and it was unlike anything we see on Earth today. Hello everyone, today we're traveling back to one of the most extraordinary periods in Earth's history, the age of giant creatures that dominated our planet long before the first dinosaur took its first breath. This isn't just a story about big animals, it's about how our entire planet's atmosphere and ecosystem created conditions for life forms that seem impossible today. Scientists studying ancient rock formations have discovered fossils that challenge everything we thought we knew about the limits of animal size. These weren't just slightly larger versions of modern creatures. They were evolutionary experiments that pushed the boundaries of what's physically possible for life on land. Today we'll explore how Earth's ancient atmosphere created these giants, what evidence we have from 300 million year-old fossils, and why these incredible creatures disappeared long before dinosaurs appeared. At the end, we'll discuss what this tells us about evolution and whether such giants could ever exist again. The story begins in the Carboniferous Period, roughly 360 to 300 million years ago. This was a time when our planet looked completely alien. The continents were arranged differently, with much of the land concentrated near the equator. But the most dramatic difference was the atmosphere itself. During this period, oxygen levels in the atmosphere reached an incredible 35% compared to today's 21%. This oxygen-rich environment was created by vast forests of primitive trees and plants that were pumping oxygen into the air at unprecedented rates. These weren't the trees we know today, but giant ferns, horsetails, and club mosses that could grow to enormous heights. The first major discoveries of Carboniferous giants came in the 1870s, when paleontologists began finding massive fossils in coal deposits across Europe and North America. These coal seams, formed from the compressed remains of Carboniferous forests, preserved incredible specimens that revealed a world of giants. In 1885, French paleontologist Charles Brongniart discovered the fossil of Meganeura, a dragonfly-like insect with a wingspan of 75 centimeters. This discovery shocked the scientific world because modern dragonflies rarely exceed 12 centimeters in wingspan. But Meganeura was just the beginning. Paleontologists soon uncovered Arthropleura, a millipede-like arthropod that reached lengths of over 2 meters and widths of 45 centimeters. To put this in perspective, imagine a millipede longer than a bathtub crawling through ancient forests. Fossil trackways show these creatures moved in herds across the forest floor. But perhaps the most terrifying discovery was Pulmonoscorpius, a scorpion that reached lengths of 70 centimeters. Unlike modern scorpions, these ancient giants had primitive lungs and could survive both in water and on land. Their fossils have been found with preserved book lungs, showing they were adapted for the high-oxygen environment. The plant giants were equally impressive. Lepidodendron trees could reach heights of 40 meters, with trunks over 2 meters in diameter. But these weren't true trees in the modern sense. They were giant club mosses with hollow trunks and shallow root systems. When they died, they fell and created the coal deposits we mine today. American paleontologists have discovered fossil evidence of Hibbertopterus, a sea scorpion that reached lengths of 1.6 meters. These aquatic predators dominated freshwater environments before eventually moving onto land as the oxygen levels rose. The biggest mystery surrounding these ancient giants is why they grew so large in the first place. The relationship between oxygen levels and arthropod size has puzzled scientists for decades. Modern insects are limited in size by their respiratory system, which relies on passive diffusion through small tubes called tracheae. In today's atmosphere, insects can't grow beyond a certain size because their respiratory system becomes inefficient. The oxygen simply can't reach the inner tissues of very large insects. But the high oxygen levels of the Carboniferous period removed this constraint, allowing arthropods to grow to incredible sizes. However, this explanation raises more questions than it answers. If high oxygen levels alone allowed for giant insects, why don't we see similar giants in other high oxygen periods in Earth's history? Some scientists argue that there must have been additional factors at play. One controversial theory suggests that the lack of vertebrate predators played a crucial role. During the Carboniferous period, vertebrates were still relatively small and primarily aquatic. The absence of large land predators meant that arthropods could grow large without the evolutionary pressure to remain small and agile. Another mystery involves the plant giants. How could these massive lepidodendron trees survive with such primitive root systems and hollow trunks? Modern trees require complex vascular systems and strong wood to support their weight, but these ancient giants used completely different strategies. The disappearance of these giants is equally mysterious. Around 300 million years ago, oxygen levels began to drop, and the climate became cooler and drier. But the extinction wasn't gradual. Many of these species disappeared relatively quickly in geological terms. Some scientists believe that the evolution of more efficient vertebrate predators contributed to the decline of giant arthropods. As reptiles and early synapsids grew larger and more sophisticated, they may have outcompeted the giant arthropods for resources and territory. The collapse of the Carboniferous rainforest ecosystem, known as the Carboniferous rainforest collapse, marked the end of this age of giants. Climate change and tectonic activity destroyed the vast coal forests, eliminating the habitat these creatures depended on. Scientists have substantial evidence supporting the oxygen-size relationship in arthropods. Laboratory experiments with modern insects raised in high oxygen environments show that they do grow larger than normal. Fruit flies raised in 35% oxygen environments grow significantly bigger than those in normal air. Fossil evidence provides direct measurements of ancient atmospheric composition. By analyzing the carbon isotope ratios in ancient plants and the structure of fossil leaves, scientists can estimate oxygen levels with remarkable accuracy. Multiple independent studies confirm that Carboniferous oxygen levels were indeed much higher than today. The physics of arthropod respiration strongly supports the oxygen limitation theory. Mathematical models show that the passive diffusion respiratory system of insects becomes increasingly inefficient as body size increases. The high oxygen levels of the Carboniferous period would have extended the size limit considerably. Geological evidence reveals the massive scale of Carboniferous forests. Coal deposits around the world contain compressed remains of these ancient ecosystems, providing a fossil record of unprecedented plant productivity. The sheer volume of coal formed during this period indicates oxygen production on a scale never repeated in Earth's history. But competing theories challenge the simple oxygen explanation. Some researchers argue that other factors, including atmospheric pressure, temperature, and ecosystem structure, played equally important roles. Studies of modern high-altitude insects, which live in low-oxygen environments, show that arthropods can adapt to oxygen limitations in unexpected ways. Recent research on fossil specimens has revealed sophisticated respiratory adaptations in giant Carboniferous arthropods. Some species developed enlarged spiracles and more complex tracheal systems, suggesting they were pushing the limits of what was physiologically possible even in high-oxygen conditions. Computer modeling of ancient ecosystems suggests that the unique combination of high oxygen, warm temperatures, and specific plant communities created conditions that were perfect for arthropod gigantism. When any of these factors changed, the giants could no longer survive. Comparative studies of island ecosystems show that isolation and lack of predators can lead to gigantism in modern arthropods. Some Pacific islands have stick insects over 30 centimeters long and spiders with leg spans exceeding 25 centimeters, supporting the theory that reduced predation pressure contributed to Carboniferous gigantism. So everyone, the age of giant creatures before dinosaurs, represents one of the most extraordinary chapters in Earth's history. We've seen how unique atmospheric conditions combined with specific ecological factors created a world where arthropods could grow to incredible sizes. Key takeaways are: high oxygen levels were crucial, but not the only factor enabling gigantism. The combination of atmospheric composition, climate, ecosystem structure, and lack of large vertebrate predators created perfect conditions for these giants. Understanding this period helps us appreciate how dramatically life can respond to environmental changes. The most important question is, could such giants exist again if we recreated Carboniferous conditions? The evidence suggests that while high oxygen would allow larger arthropods, the complex ecosystem that supported true giants might be impossible to recreate in our modern world. Let me know in the comments, would you want to visit the Carboniferous period if time travel were possible? Do you think giant insects could survive in today's world if we could somehow increase oxygen levels? In the next episode, we'll explore the Great Dying, the most devastating mass extinction in Earth's history that occurred just after the Age of Giants ended. This event nearly wiped out all life on Earth and paved the way for dinosaur dominance. If you found this video helpful, don't forget to like it and subscribe to the channel for future episodes. If you want to learn more about ancient life, related videos are linked in the description.